Hello and welcome to C Programming 0 to Neural Networks. In this part we are going to be building a visual neural network visualizer in SDL2, and we've not covered how to build neural networks yet. We've not got that far. We're sort of going through the C programming language bit by bit at the moment, but we are going to be using SDL once we can build a neural network to visualize how the neural network's activity, and we're going to use that to sort of train image data and that kind of thing. So just as another run through of the SDL environment, going to go through that a little bit slower than we did in the Snake game, and we're going to build this. We're going to build a sort of a general architecture sort of visualization application, or at least the easiest implementation, the simplest one, and we're going to build on that and try and make it better as we go through the series. So we're doing version 1 of Neural Network Visualizer in this part. So let's go get right ahead and build it. So let's start by making what we're going to call it drawnet.c is what we're going to call it, and we're going to make, because whenever I do SDL I like to include a separate header, so we're going to do drawnet.h, and then we're going to make a main function and obviously return a 0, and then we need to make our drawnet.h where we're going to include all our libraries. So we're going to do include, we're going to need the standard input output library. We might need the standard lib, I'll throw it in anyway, and we'll probably need standard bool, and we'll definitely need to include SDL.h. Now if you've tried using SDL before, you might be tempted to do SDL slash SDL2 slash or something like that way around. It's better practice to just include SDL and then put the include path for where SDL lives on the system. So we just do SDL.h. Now, if you've installed SDL and you've not used a SDL graphics library before, when you install it, say you install it on Arch Linux, pacman -s SDL2, I think you do. Yeah, and I've obviously already got it installed, so I'll cancel that. Where does that get installed to? It gets installed to user/include SDL2, and then all the SDL files are in here. So we need to include that path. It's not part of the C standard library, so we need to specifically include that path. So if we wanted to compile this now, we'd have to do gcc drawnet.c minus link SDL2. We also need to do minus -i and then /user/include/SDL2 / and then the program will compile. But we don't want to have to type that out every single time we compile. So whenever doing an SDL application, I make a makefile. So let's make a makefile. So let's rm that a.out. So we're going to do mvim makefile. You need to have make installed to use makefiles, but obviously again on Arch Linux you just do pacman-make, I think, or dev tools or something like that. It's in there somewhere. You can search on the internet for it. Makefile. Obviously, if you're not using Arch Linux, if you're using Debian of some kind, then you obviously have to check where SDL gets installed to and those kinds of things. Generally, you're going to be user/include/SDL2, and if you're on Windows, obviously it's a little bit different. But the good thing about SDL is that it's cross-platform. It'll work on Mac OS, it'll work on Windows, and it'll work on Linux. So that's one of the reasons why I'm using it for this series, because it's most of these programs that we're going to make, in fact pretty much all of them when we do neural networks, are going to work on any platform, and I think that's important because not everyone's using Linux. I would recommend it though. So how do we make a makefile? Well, we need to set some variables. So we do cc equals, and this is the C compiler that we're going to be using, and we're using GCC, and then we do C flags equals, and then we can put any flags that we want in, for example warnings all minus warnings extra, so we can stick our C flags in there. We'll leave them in for now. Then we've got libs. We're using SDL, so we need to link SDL2 minus in front of that, and then if we wanted to link math lm and so forth, we put all our libs in there. And then we need includes equals, and then we do the minus capital I, and then immediately afterwards we do the path of our SDL that we're including. So /user/include/SDL2/. And then we need our sources. So our source file is drawnet.c, and then we need to make object file, so we do objs equals $sources :.c equals .o, and then we do main. We specify the output that we want for our when we compile, so we don't end up with a.out, we end up with actual application name. We're going to call it DrawNet, and then that sort of sets up all our variables. So now we need to sort of build all that. It takes a bit of learning to learn Makefiles. They are very useful to learn, though. I've quite liked Makefiles these days. We can do lots of build scripts. We can just use a shell script to make a build script. We could obviously just copy and paste what we typed in before into build.sh or something. You can do it that way, but I like the make and make clean. Once you've set all this up, it's really quick to use, and you get used to using it, and it does work quite nicely. So we need to do main : obj, and then we put all this together. So we do cc c flags includes minus output main. We do that for all the object files, and then we do libs. So that'll compile, well, that'll create object files, and we want to build those object files into an application. So we have to do .c, .o, and then we do the same thing again almost. C flags includes, instead of doing -o, we do for C, other way around, and then O, at symbol, so less than sign, at symbol after these dollars. You can read up about Makefile syntax, but I'm more for just memorizing this kind of stuff. And then we do clean rm *.o, so this will remove all the .object files, and then asterisk, we want to remove the actual output executable file. So all being well, we can now build the application by typing in make, and if we type make clean, it will remove all the object files and the executable files, so we go back to just the source code again. And that's why using Makefiles is handy, for that one reason. We can obviously build a shell script and mimic that behavior as well, but once we've got a Makefile, if the application gets more complicated and starts including more source files and those kinds of things, we've got all this laid out nicely, and we need to add more libraries, or we need to add more include paths and so forth. It's all just in one place, so it is quite a handy build environment and a build tool. So let's get on with making this. We need to make this now. STL, we can draw lines, we can draw squares, and we can draw points, but we haven't got a circle function built in for some unknown reason. I don't know why they don't just include a draw circle function, but we're going to have to make a draw circle function. We'll get to that shortly. So drawnet.c. So let's go through making the STL environment, setting up the STL environment. So the first thing we need to do is we need an STL window, and we have to do a pointer to something, and I usually call it window. You see a lot of programs where it's just W, they could just call it W, which is probably less to type in, but it's not like you need to reference the window too often. And then we need an STL renderer. Now you don't have to use STL renderer. There's different ways you can use STL. You can use surfaces and not bother with a renderer at all, but it does give you hardware acceleration if you've got hardware acceleration available to you. So it's probably better to learn STL renderer than just STL surfaces. And the rendering, the way we do rendering with a back buffer and a front buffer is exactly how OpenGL works and exactly how lots of other things work. So if you're not overly knowledgeable about graphics libraries, using the STL renderer means that you're learning the sort of the most used way of using a graphics library. Basically, you're going to find the same kind of paradigm in lots of other things, so it's useful to use. So we need to initialize with the STL init video we run, basically, to initialize STL. Now we wrap that in an if statement, and we say if it's less than 0, then there's been an error. So we do printf stderr error STL init video. So this prints out an error message to the standard error rather than the standard output, just saying error STL init video. So this basically, if this is less than 0, it means something's gone wrong. So that's how we sort of get the environment set up. Now we need to initialize our window. All we've done is create a window and create a renderer up here. So we need to initialize the window and initialize the renderer. So let's start with a window. We can do window equals SDL create window. And we can look at what this function does. We have a SDL create window, so we need a title, which is a const char star, and then we need an int x, int y, int width, int height, and then uint 32 flags, basically just flags. And there's lots of flags. I usually do for most applications if I'm just making them in the first instance. SDL window borderless, so just no window decoration. So that's what we're going to be using here. So that's the signature of the function. That's what we're going to be following. So we'll do, I like to split this up. Title, we won't bother putting a title. We're going to do window X, and we're going to define these up at the top. And we need window Y, window width, and then window height, and then finally SDL window borderless. SDL window border. So let's make them up here now. So make sure this program works in the first time. Window X, window Y, window width, and window height. So I've pretty much got this memorized now. I'll try and make the window so it matches this streaming setup. So I think we do 10 minus 20, width is 1770, and 1410. I think makes a square that fits perfectly here. Well, we'll soon find out, won't we? Now, after we've created our window, we also want to check that that worked okay. So we need another if and another f, print f, and we're going to print out another error, standard error, not window, and we're just going to check not window. Basically, if this window is still pointing to null, that means that this didn't work. So we can check it nice and simply with just doing an exclamation mark window. And then we need to create the renderer. So we do renderer equals SDL create renderer. And look at this function signature. So SDL create renderer, we need to put the window in. We need an index, and then we need some flags. And the window is obviously the window that we've just created. The index, the index of the rendering driver to initialize, or -1 to initialize the first one supporting the requested flag. So we use -1. And then the flags, there are a variety of flags. Where can we find them in here somewhere? Well, this is what I use, SDL renderer accelerated, which is there. I think there's got to be a list of them in this man page somewhere. There we go, SDL renderer software, SDL renderer accelerated, SDL render, present vsync, and so forth, target texture. So we're going to use SDL renderer accelerated. So we do window -1, SDL renderer accelerated, can I spell it? ACCLERATED, accelerated. And once again, we want to do basically the same thing. We want to do if not renderer, error not renderer, and that catches all of our errors. And then at the end of the program, once we've done all that, we need to clean all that up. We need to free all that memory before the program exits. So we'll do that before we do anything else. We have to do SDL destroy renderer. And then we just put the renderer in there. Then SDL destroy window, and then finally we run SDL quit, which because we initialize this SDL in a video, so that just destroys everything else that's left. And let's make sure we've got no compiler errors. I'll put renderer instead of render. 30G renderer equals. What have I done wrong? Error. Renderer undeclared first use in this function. Renderer. And we've got to have spelt it wrong somewhere. Go back to the top. There we go. And if we run it, it almost does something and then doesn't do anything. So what I usually do at this point is do SDL delay and stick a delay of 2 seconds. This is in milliseconds, so we do 2000 for 2 seconds, and then we're going to draw like a color on the screen. So we do SDL set render draw color. And the first parameter is the renderer, and then we need to put the colour in it. There's 4 parts to a colour, so there's the red, green, blue, and then A, alpha channel, which is the opacity. So and they're all 0 to 255, so as in the hexadecimal range, so we can just put 0, 0, 0, 0, or 255 for the opacity, and that'll make black. Or if we do 255, 255, 255, that'll make white. Now, I prefer hexadecimal notation for these kinds of things. So if you do 0x for hex, then you can use like FF. 0xFF, 0xFF, and that's FFFFFF, which is white, isn't it? So let's make it green. For now, just to make sure everything's working, then we have to do SDL render clear. And then we put the renderer in there, and then we do SDL render present, which will present anything we've drawn to the screen. Let's see if this works, and now we've got a green screen. We could use that for OBS Studio for our green screen, couldn't we? Right, so that's pretty much SDL set up now. So we've got our environment working. We've tested it. We're not getting any errors. So what we want to do is we want a main program loop that's going to sort of keep the program going rather than just hanging around for 2 seconds and then quitting and ending the program. So we need an event loop is what we call it. So what we need to do is we make a bool quit equals false, and then we need to while not quit. So as soon as quit becomes true, this while loop's going to end, and we're going to use that for the exit condition for the program. So we can get rid of this SDL delay now. We need another while in here that's going to detect key presses and events and those kinds of things. And we have something built into SDL called SDL event. And we're going to need to make one of these, and we're going to call it event. And we're going to while on that as well. So we do while, and we do SDL poll event. And we have to put the address of the event that we've created. There's another way to do this. We can do SDL wait event. So SDL poll event continually polls the sort of keyboard or any input events. I think it does it every 10 milliseconds, and it continually looking for events. But that does use a bit of processing power. It has a processing overhead attached to that, so we usually put an SDL delay of like 10 at the end. I'll do that in a bit. But it uses a lot of processing power, continually polling events. SDL wait event, it'll only do anything if you press a key. But obviously, if you're making a game in SDL or something, you want stuff to be moving around in the background all the time, then you need to use SDL poll event. So anyway, we're obviously not building games here. We're building neural networks, but SDL is great for making games, apparently. I've made a few 2D games in it, but I'm not really a big games developer or anything like that. I used to make games when I was a kid, though, didn't we all? So we need to switch on the event.type and the various sort of built-in events. So one of them is case SDL quit. Now that event is the say if you've got an X on the top of a window and you press it, it detects that event. Or if you press Alt F4 on Windows, it detects that event. I use i3, and that's Alt Shift Q. It detects that event. So all we want to do if that happens is set this quit to true. True, and then this will quit out of this while loop and end the program. So this program will now persist in memory, but really we want to detect a key press as well. I usually use escape to be the quit in an SDL application. So we can do other cases. We can do case SDL K, SDL key up. So this detects when a key is released and pushed up. And we're going to do nothing for that. We're going to put it in anyway, and then we're going to do SDL key down. This detects a down key press. So this is when we press a key down. So there's two separate events. Pressing a key down and releasing a key are two separate events. And we're only going to be looking at SDL key downs. So we need to do another switch inside this on the type of key that was pressed. And to do that we do event.key.keysim.sim. So that's quite a bit to remember, that, isn't it? Now, there's a reason why it's sort of broken up into these four parts, but for now, I would say just remember to type it out like that, because it's not like you use it for anything else in SDL. It's just for detecting key presses. And then we can do our key presses. So we've got SDL K K for key press underscore escape escape break. So that's when we press the escape key, and we can do quit equals true. Obviously we can detect any other key press as well. We can do SDL key K underscore lowercase a, and that'll detect a lowercase a. Uppercase a, that'll detect an uppercase a, and so forth. 0, that'll detect the 0 key, and so on. So we can have different events for every single key press that we can do. There's also a text input which just detects text input as well, which is handy for if you're building something like a text editor. So that should do it. So hopefully we haven't made any mistakes. Type that in wrong, and now if we press escape, the program quits, or if we press alt shift q, the program quits. So the program now persists. So we've got a proper environment set up now. So next we want to change this color from being green. Probably want to have like some kind of dark background or something, and we want to actually build this this pattern here. But well, to build a variable architecture network where we can type in any numbers, and then we can type in like 2 input neurons, 2 in the middle, and then 1 at the end, or we can have 10, 10, 15, or whatever. So that's what we're going to be building here today. So what we need is to move all this stuff that we're drawing the screen into our render loop, so we continually redraw the screen after we do anything. And I usually put the render clear at the top and then reset the color at the bottom, and then we do start render loop and then end render loop for a bit of a shorthand way to do it. Things get more complicated in our render loops. If we need if we've got physics engines and we need to be bound to time and we need exacting frame rates, we have to do things like get ticks and all. There's a lot more to SDL than we're going through here. And there's a lot more to SDL than we're going to need for neural networks. We won't need to do those kinds of things. Really, we're just using it as a graphics library to visualize this kind of stuff on the screen, so we can better understand neural networks and understand how they work, and get the neural network to interact with this graphical layout, and so we can see which neurons are firing the strongest and which connections are the strongest and that kind of thing. That's the main reason why we need a graphics library in this series, and we'll start by building neural networks just in the terminal, and we'll just train terminal data. We'll just be training numbers and that kind of thing. But it won't be long before we start wanting to, once we've got a sort of a neural network framework kind of working, we're going to want to train more interesting data, and we're obviously going to need a graphics library to be able to do that. So hence this video, and hence this continuing focus on SDL2. So what we want to do is make a function, let's call it render network. Now we're going to have to pass the renderer to it so we can draw things to the screen, and then we're going to want our network now to take up the entire screen. We want it to be in some kind of manageable box, so we're going to need net x and net y, which we're going to specify up here. So let's do int net x, int net y, and they're going to have to equal something. Well, first of all, we want to define the size of our network box. Define network width, and define the network height. So let's make it 1100 by 1100. Let's make it square for now, and then we can use these defines to figure out how to center our network. So we've done this in the Snake game already. We want to do window width divide 2 minus network width divide 2, and this should always put us in the center of the screen. We don't really need to put the brackets in, but I do like to, it makes it a bit easier to read when we're just skimming through. So we can pretty much copy and paste that and just change this to y in height, can't we? Height, network height. So that should put this render network thing in the center of the screen, or based on, well, these coordinates are already filled out. So let's just draw a box first of all. Let's make sure everything's working and do void render network return, and we're gonna need to receive the SDL renderer, which is a pointer to a renderer, and we're going to need int x, int y. So to make a box, we use SDL rect, and we have to make an instance of these rect. This is a type, so we'll call it box. and then we can specify some parameters. So box.width, box.width, box.height, box.x, box.y. So the width is going to be network width, the height is going to be network height, and the x is going to be the x that we've passed, and the y is going to be the y that we've passed. We need to set a color so it looks like a different color. So STL set render draw color, renderer, and then 0x0. What color do we want to make our box? Let's make it green again. I think we've made the background back to black, didn't we? No, we haven't. Let's do that now. Let's make the main background 1 1 1 1 1 1, and we're going to make our network box green just to confirm it's working. So we just need to draw that now. STL render fill rect. We've got render fill rect or render draw rect. Draw rect just draws the outline of a square. Render fill rect fills the entire thing in with the color. So we do renderer and then the address of the STL rect that we've just made that we called box. Let's see if this works. Where was it? 22. Renderer. And there we go, we've got a box in the center of the screen, and we can change the parameters up here. So if we want to make this bigger, in fact we probably should. So we do the width as 1600 and the height is 1300. We want to make it take up most of the screen. That'll do us. And I think we change this to draw, and we change the color to say 55, just like a mid-gray. And we'll leave that in for now. Yeah, so there we go, we've got our a square. So we want to draw this pattern inside this this kind of box. Right. So in order to do this, we're going to need to draw circles, aren't we? And as I mentioned at the start, in STL we don't have a STL draw circle or STL fill circle. Got to make them ourselves. STL is called a Simple Dynamic Media library, and it is very simple. It's very powerful. It's cross-platform, but it doesn't include very much into that you might get in some graphics libraries. Where you can draw circles and you can do all sorts. If you want to draw a circle in STL, you need to make it out of the stuff that it comes with, which is drawing points, drawing lines, and drawing squares. So you can think of there's lots of different ways to come up with drawing a circle in STL. I use a pretty standard way. So let's make our function. We're going to stick with the STL convention. We're going to call it STL render fill circle. And return. And what we're going to take is the STL renderer. We're going to have int x in x position, int y position. We're going to have an int radius, and we're going to pass a color. So we're going to do STL color C. So we're taking quite a few parameters there, but the main thing is the x, y, and the radius. And how do we do this? We have to do 2 for loops. So we do for. Now you can work out the trigonometry of what's going on here if you want to. I'm not going to go through it here. I'm just going to do it quickly just so we can get on with the video. But as I said, there's lots of methods for drawing circles. It's actually quite a bit more code to draw the outline of a circle than just to draw a filled circle. We're only drawing filled circles here. So this is how you do it if you're interested. You do int w equals 0. W is less than radius times 2, W++. And then you do int h, height equals 0, height is less than radius times 2, that should be 2, height plus plus. So that's how we set up our loops. And then we need a dx and a dy, so we need int dx equals radius minus w. And we need int dy equals radius minus h. And then we do an if. I can explain what it's doing, but it's really, you need to draw it out on like graph paper or something to really get your head around. It obviously involves a bit of trigonometry here, or shorthand trigonometry anyway. So we do if dx times dx plus dy times dy is less than or equal to radius times radius. And then we do STL render draw point. Renderer, and then we do x plus dx, y plus dy, so it's in the right position. And that will pretty much do it. Obviously we need to set the color as well, so we need to do STL set render draw color, and then we've passed this color over here, so we're just going to get those values. So we're going to do c dot red, c dot green, c dot blue, c dot alpha channel, and hopefully that'll work. Let's give it a try. We need to make a color, STL color c dot red equals 0x ff. Shall we do a red circle? GBA 0 0 0, and we can do STL render fill circle, and we pass the renderer, we pass x, y, in fact we pass the position x plus 200, y plus 200, and radius 150, and then the color is C. So this should STL set have too few arguments. Oh, I haven't passed the renderer. 13. And now we get a circle. So that's how you draw a circle. You have to do a fair bit of work to draw a circle in STL, unfortunately. But once you've got that function, you can obviously, it's a flexible function, you can use it however you want. You can draw as many circles as you would like. This way of doing it, just as a quick note, this is not very good for really big circles. It's not very. It's efficient for small circles like we're going to be using in neural networks, but if you wanted to draw like a big circle on the screen, that's probably not the best way to do it. As I said, there's lots of different implementations of drawing a circle, so really it should be STL render fill circle small because it's only really appropriate for small circles, otherwise you're doing too many calculations, but so be it. This will work for our purposes. Right, so what we need to do now is make an architecture for our network, so let's do that. So what we want to do is we want an integer array to store the values for how many neurons we've got in each layer. So we're going to do int arch, short for architecture. It's going to be an array, and we're going to make this a global variable just so we can get it anywhere. And to make this diagram, which we're going to do first, we'll do 2 2 1. So we're initializing it as 2 2 1. So two input neurons, 2 neurons in the middle layer, and then 1 output neuron is basically how we would describe that. So we're going to need to find some way of ascertaining the size of this array, aren't we? So we're going to need an array length. We have actually covered this. Macro. So size of x divide size of x at position 0. Size of the entire array divided by the size of one element in the array. And that will give us our array length. So let's go back to our render network. So we can drop that down. In fact, we're definitely going to need the color, so we may as well put that there. We're going to need a loop, aren't we? So we're going to need first of all, we need to run that array length macro and get the number of layers we've got. So int layers equals array len arch, and that will give us how many layers there are in that architecture that we've just made. And then we're going to for through them basically. So we're going to do int I equals 0, I is less than layers, I plus plus. And we're going to draw a circle, but we need to figure out the sort of x positions of each layer. So we need to sort of divide the network, the entire width of the network window by the number of layers we've got to sort of divide it into an appropriate number of columns. So what shall we call that? Int layers width, int layer width, let's call it. And we're going to go network width divide layers, and that will give us a network width that we can times by our I as we cycle through. Now, we'll do it to show the problem. So if we put our draw circle function here, instead of doing x times 100, we're going to do I times layer width. Now when we do this, our sort of neurons are right over on the edge. We want them to be in the middle of each layer, not right at the start of each layer. So we need to find the midpoint in each layer, don't we? So what we do is we do layer, what shall we call this? Let's call it x offset. And all we do is we do layer width divide 2, which will give us a halfway point. And we're just going to add that onto this calculation here. This is getting a bit big now, so what we're going to do is we're going to do int x pos equals x plus I times layer width plus x offset. And we're going to replace this with x pos. Hopefully that will be everything's centered now. And then this is already flexible. So if we added another couple of layers in here, 3, 6, 3, 5, then everything sort of lines up perfectly. And this is exactly what we want to get to. It is a bit tricky working with this kind of graphics programming. We're going to end up with one giant loop here that kind of makes all this work. But there may be better ways that we can come up with the implementation. There's certainly easy ways to draw these neurons. We can split it up into different functions, but then the difficulty becomes in drawing the lines, the connecting lines, you see. So that gives us our xpos. And now we want to do another loop where we go through the number of neurons in each layer and then adjust the y position. So we've only looked at the x position so far. So now we need to look at the y position. So we're going to do for int j equals 0, j is less than arch at position I, j plus plus. So arch at position 0 is 2, arch at position 1 is 2, arch at position 3 is 1, and so forth. Sorry, 0, 1 and 2. And we're going to basically loop through how many neurons we've got in each layer and try and space them out just like we've done with this sort of x kind of offset and layer width. We want a sort of a neuron height width and so forth. So we're going to have to do that as we go as well. We're going to have to do that sort of in place inside this loop. So we need an int, what should we call it? Neuron height equals network height divide arch at position I. And then we're going to need to do a y offset equals neuron height divide 2. So do the same thing again, and then we should be able to calculate y position. Now y pos equals, it's going to be very similar to what we did before. How are we going to do this? We're going to do y plus j times neuron height plus y offset. Should probably work. Let's find out. Y pos. No, unused variable. Put this in the wrong place, haven't I? That needs to be inside there. And there we go. We've got ourselves a network. We've almost done it. We've almost done it. We obviously haven't got any connecting lines. They're too big as well, so we'll just drop. We're going to vary the size in a bit. Let's put them down to 80. And let's make them green as well, so they actually match the diagram that we've got on the screen. So we do 0, 0. We're getting there. Look at that. Almost the same. So what about these connecting lines? So all we've done here is we're just reading an array and then offsetting these into the right places by doing a bit of calculation on the width and the height of the window that we're provided. And obviously another way in this is flexible because it's all based on this window width. So we've made this like 600 by 600. Everything would sort of scale down accordingly apart from the size of the neurons. So what do we have it as before? 1600 by 1300. Make sure that's the right size. Yeah, it is. Right, so now we need to draw the connecting line. So what we have to do when we're at this neuron, we want to look ahead and look at how many neurons we've got in the next layer, and then draw a line from where this one is to where this one's going to be. And we need to do that before we draw the circle, because we want to stack the circle on top, so we haven't got lines drawing over the top of the circle. It's quite a challenging little thing to do. So we need to, when we're here drawing this one, we need to loop through every single one of these and draw a line between them. Then we get to this one, and then we do the same thing again. We loop through and we draw a line to that one, and then we move to the next layer, and then we draw a line to this one. Obviously, when we get to this, there's no more layers afterwards, so we only want to do that for the layers up until number of layers minus 1. So let's do this. This is a bit of a tricky part. So we need another loop, don't we? We need a for. I'm going to go for k, int k equals 0, k is less than. We need to actually wrap this in an if, don't we? Because we can't do this for the last layer, because we're going to do arch I plus 1. And obviously if we do that on the last layer, then the program's going to crash. K plus plus, so we need to do an if. And we're going to do if I is less than layers minus 1. And this will loop through all the neurons in the next layers, and we need to work out our x position and our y position for each. So we kind of need to repeat what we've done here. We're going to end up with loads of intermediate variables, aren't we? Again, this is the first kind of single loop version of doing this, and it shows how tricky it is to achieve actually just drawing out a network on the screen. It's actually network visualization is almost as hard as building neural networks. Well, there's less maths involved, but there's more intermediate variables. Right, so how do we do this? We have to do, we have to figure out our layer width. Well, that's actually quite easy. So the xpos, we're going to make an xpos2. xpos2, and this is just simply plus 1. So we're moving this along one, so that's going to get us into the right column. So xpos2 is that easy. ypos2 is going to be a bit more difficult. So how are we going to do ypos2? ypos2 equals y plus j, well, we need plus k times neuron height, and we need a neuron height 2 and a y offset 2, because these are going to be different for these, aren't we? So we need to do these again. Neuron height 2, y offset 2, and this is going to be arch plus 1, because we need to divide the network height by the number of neurons in the next layer, and then the neuron height is just going to be that, isn't it? Neuron height 2 divide 2. I reckon that'll do it. We're about to find out. We need to STL draw line now, so let's do that. STL render draw line. Doesn't it look all really messy though? It's not a very nice programming this, is it? But it does work. What are we doing? X pos, Y pos, X pos 2, Y pos 2. Probably want to set a call at STL set. What colour shall we do the lines? Let's do them also in grey. Let's find out if we made any mistakes. Yeah, of course we have. What's wrong with STL set render draw colour? '71. I'm in the right line. Set render. Oh, renderer. And then Y pox. Y pos. And now we've got connecting lines after doing that. So what we had to do, just as a quick reminder, for every neuron we have to figure out the position of the neurons in the next layer and iterate through them one by one and draw a line to that one. And then we do the same thing for this one and the same thing this one. Then the loop moves to the next layer and we do the same thing for this one and the same thing for this one. And now we're done. We've made the program. We're going to make one more change as we're about to find out why. So if I put 22 neurons in the middle layer, then they all sort of overlap, don't they? It doesn't look very good. So we're going to change that. We're going to vary the size. So at the moment the size is fixed at 80. So what I've been doing is doing int size equals, and let's say 80, let's make it 100, divide arch I, but divide the number of neurons in that layer plus 2. And then we put size. We make a plus 2 just to make it so they're not 0 size. And now the size of them decreases when there's more in the network. So let's make a really big network. Let's do 12, 25, 66, 6, no, 4, 2, that'll do. Hopefully this will all work. Yep, it all works. We've got a neural network visualizer now. And that's how we build a neural network visualizer. Isn't that complicated? Now you'll notice this same problem. This gap here is, I made this in one of my videos. I got a little bug in the program. I obviously fixed it straight away, but this is how you fix it. So we need to cast these to floats. Well, we do need to spell float correctly. We need to cast this to a float, and then we need to change all these intermediate variables to floats. So they only get used as an int right at the end. And this kind of fixes everything. So, because obviously we're dividing things and times and things together, so we're dividing there. Actually, we probably only need to change the ones where we're doing division, but I'll change them all because I've pretty much done it all now, haven't I? Yeah. And now everything lines up correctly because we're doing all our divisions correctly. We're not losing the bit off the division when we do an integer. So let's make an interesting looking network. I won't make the brain again. Let's do a realistic network of what we can train without any hardware acceleration. So we could have like 12 inputs going into 24 neurons, going into another 24 neurons, going into 32 neurons, going into 10 outputs. We can comfortably make this on a running on a laptop or something. And there's a lot of parameters here. I'm not going to calculate how many it is, but obviously we know that the large language models, the big supercomputer ones, have got like trillion parameters and billions of parameters, tens of billions of parameters. But for a home computer, you can probably about manage 1 billion parameters. Unless you've got a bit of graphics acceleration and you've implemented graphics acceleration, then you can do maybe 10 billion parameters, but there is a sort of an upper limit to how many parameters you can get. We'll start by doing, well, we won't even start with networks that complicated. We'll start a lot simpler than that. So we'll start by doing this kind of thing, which will train fast at the very least. But it takes a while to build up to using more complex input data and output data. Obviously, it's I've mentioned before that it's all about, it's quite tricky sort of designing your inputs and your outputs. That's what it all comes down to once you've got a neural network implementation. But it doesn't, I think just visualizing neural networks looks quite cool. It's kind of got an artistic sort of thing about it, all the sort of patterns that get made in the connecting lines and that. And it's really good watching them train when you set them to sort of change colours and that kind of thing. I usually go for a blue theme, but I just wanted to match this. Let's put it back to what it was on the screen. So it's 2, 2, 1. 2, 2, 1. Done. Made. Completed. They're not very tutorial video. That's not very explanatory. And I just wanted to go through this kind of like frustrating implementation of doing this. Let's get rid of a bit of white space. So this is our way of doing it, and it does work. And I want to improve my visualizations for neural networks. So I've started thinking about, shall we do an example? Let's say you've got, go up to like 120 neurons in a layer on a laptop. But it looks ridiculous, doesn't it? And if you've got another layer going into maybe 48 neurons, it's just a big block, just a big mess. You don't really derive any information from it. There's almost no point in rendering it, is there? So I've started thinking that maybe there's better ways to visualize a network. I just did a kind of a throwaway visualization. I just wanted to see what the network was doing, and I just wanted to see the whole training process and confirm everything was working okay when I first started visualizing neural networks. That was my only really goal. But now I think it's quite an important part of, certainly for this series, but also for me, understanding sort of better architectures for networks. We can, for example, once we get to putting in activation functions, we can have varied activation functions throughout the network. We can have a layer of sigmoid going into a layer of ReLU going into a layer of something else, going into a layer of softmax. And it would be nice if we could like somehow visualize that in the visualization. And when we get like, when we're using lots of neurons, there's all, like I say, no point in sort of visualizing them all. Certainly not all these connecting weight lines here. That it's just a block, isn't it? It's a waste of time. So there's got to be better techniques for visualizing this. I was thinking of maybe like condensing, when there's lots of neurons, condensing them into like a smaller block and then having a number representing how many neurons there are in that. So basically I need a version 2 of doing this, which is one of the reasons why I'm going through version 1 now, just to show you where we're up to with this in this series. Because it's more important to actually get the neural network to do useful things and be artificially intelligent. The visualization of it is a secondary concern. But because it's important for the purposes of learning, and I've realised it's important for my own understanding, and it definitely matters for this series. Obviously this is YouTube, this is a channel, this is a video series. Visualization is very important, so we need to do lots of visualizations with networks. I can definitely come up with better, some kind of better implementation of doing this. Although this works, it's flexible, and it looks quite cool. So basically the problem is we have a network sort of specified like this as an architecture, and we've just got an array. So we can do whatever we want with it, but if we want to draw connecting lines, then the easiest way to do it is in just one great big sort of triple nested loop in one function. As soon as we start splitting things up into different functions, then we have to create ways to store the coordinates of all the neurons. I haven't decided how to go about doing this yet, but I think this is what I'm going to be doing for the rest of my evening, which is why I made this video. I just thought I'd do another graphical run through. Only the first bit that we went through here is really relevant, the setting up SDL. And I suppose this is useful. We're going to be using this a lot when we visualize neural networks. We use our SDL render fill circle. And I don't think there's much point in going through this, because this is not going to be a graphics programming series, we're a neural network series. But yeah, you can pause on the screen right now and then type that out, and then you've got yourself a SDL render fill circle. In fact, I'm sure it's on the internet somewhere. If you just typed in this function signature, I think this is a pretty standard implementation. They should include it in SDL, I think. Well, they should maybe figure out a smarter way than I've come up with here of drawing a circle, something that's a little bit more efficient for bigger circles, and just include it in the implementation. Oh well, they're not going to do it just because I made a video saying it, are they? Right, so shall we finish on a good pattern? Then go back to the brain. Remember in the second part, I made a neural network that looks like a brain. It was 2, 6, 12, 24, 12, 6, 1, 6, 12, 24, 12, 6, 2. I think that's what it was. Yeah, that's exactly what it was. It looks like a brain because it's got 2 hemispheres. And it's the stupidest neural network ever. So I'm going to start covering in some parts very soon neural network architectures, and start bringing in some terminology that we use in neural networks, and do it. I'm doing everything from a programming perspective. I want this very much to be a programming channel rather than a theory channel. And but this is a feed-forward, fully connected neural network is what we're looking at here. And every neuron in every layer connects to every neuron in the next layer. So imagine if we had 2 inputs with some maybe coordinates for some image data, and they get sort of broken up into all this complexity and all these weights and biases and neuron activations holding all that data somehow. And then we condense that down to a single neuron, and then we open that back up again into loads of complexity and go to 2 output neurons. We pretty much lose everything here in this kind of bottleneck. But how I imagined it when I was thinking of a brain was like, this could be like a visual input, and this could be like an ear or something, audio input, and then this could be the right ear and the right the right eye and the right ear, and this condenses down into something more complicated than a single neuron. It's like a brainstem. That's what I was thinking. But as a traditional neural network, this is like the most ridiculous architecture you could ever program. Right, we'll call it a day. Is that an hour? Yeah, 54 minutes. Yeah, not the most riveting of videos, but it's if you're following this series, trying to solve this problem of just you don't even have to use circles if you don't want to use a circle. Just use any graphics library. You can even do it as a web page in JavaScript and try and visualize a neural network. It's a good exercise and it'll definitely teach you something about neural networks because the whole sort of tracking the next layer and everything connecting together is an important sort of programming style that we're going to have to use eventually. Right, so there we go. Next time on C Programming Zero to Neural Networks, we're going to carry on with the C series. My internet connection, you'll notice I've not made any videos for about a week. My internet connection is ground to a halt. I think it's finally getting fixed in 2 days' time. And I'm uploading a video now. I'm on pointers and is at 80%. And I think I started uploading it about 16 hours ago. So that's what I'm working with at the moment. So. Yeah, I'm a bit disconnected at the moment. I can't really search on the internet or do anything. So, hence this video. Right, I will see you next time.